Hi guys, welcome to another new video from Bioorganic Hub. So in the previous video we discussed about Favorskii rearrangement. So this will be an extension of Favorskii rearrangement. So we ended in the previous video that there is a bond migrations, which are type of Favorskii rearrangement, which is called quasi-Favorskii rearrangement. So this is a serious short topic for chemical science. That's why you have to figure it out how to solve the problem on this topic. That's why this video encourages to learn about the quasi-Favorskii rearrangement. So Favorskii rearrangement is actually, this one, the Favorskii rearrangement, that you have the reactant like this, that is cyclohexanone with the substitutions of chlorine in one ortho position. So another ortho position having the hydrogen, which is actually acidic because it is adjacent to a carbonyl group. So any base will attack this hydrogen and it will create a negative charge, which is here, and this will form a epoxide ion like this, epoxide intermediate, sorry, not ion, epoxide intermediate like this, and upon nucleophilic attack this will form this type of compound. So here Favorskii rearrangement goes through two steps mechanism. One is the analyzation and then intermediate epoxide formations, and then another nucleophilic attack to the carbonyl carbon to break out the epoxide ring. Now as the name suggests, quasi-Favorskii rearrangement is a type of Favorskii rearrangement, but where instead of a lone pair in quasi-Favorskii, a bond pair is actually migrated. So in quasi-Favorskii rearrangement, it involves alkyl shift with a concomitant nucleophilic attack of any bond, any carbon-carbon bond, nucleophile actually is carbon-carbon bond, to displace of an aligned leaving group. So here also one negative charge is going to be attacked here to displace one leaving group. This is the leaving group. But in this case, this is the typical example of the quasi-Favorskii example of this one. So in this case you have a bond which will migrate to leave out this leaving group. Now to understand that, we have stated an important statement, that concomitant nucleophilic attack and to displace the aligned leaving group. So this is the main theme you have to understand for quasi-Favorskii. Aligned leaving group means you have to figure it out for a cyclohexane ring, what the bond, what nucleophilic CC bond is actually can attack to leave out aligned leaving group. So to figure out that one, you have to draw chair form or boat form sometimes for a cyclohexane ring. Like this we have drawn for this compound. To do the quasi-Favorskii rearrangement, when you have one base, so base will take OH, hydrogen of the OH group, and create O minus, this one. So and this CH3 is beta position, so this is above the plane, and this is O minus below the plane. This OTS is alpha position, so this is the below the plane. Now this bond actually is exactly parallel to this bond COTS. So OTS is a good leaving group because of the negative minus charge stabilization with the aromatic moiety of tosyl, means of tosylate. So that's why it is a good leaving group. So this bond will leave out. So what is the parallel bond? You have to mind only the parallel bond can act as a nucleophile to displace one leaving group. So this is the parallel bond of this one. So this will attack here and this will leave out. So this will form this type of compound. Now we will try to solve one important questions for GATE 2015, which was on the topic quasi-Favorskii. The question was like this. So you have the reactant like this, and you have reagent lithium aluminum hydride. So what does lithium aluminum hydride does? So it is a reducing agent. In presence of unsaturation, in presence of a double bond, it can reduce a carbonyl compound. So on looking at the compound, you can see that, you can figure it out, you can answer it that okay, you have double bond, it will not be reduced, and you have carbonyl group, it will be reduced. But there is a trick actually. That's why it has appeared in GATE 2015. You have a Br atom. When in the intermediate, what is the lithium aluminum hydride reductions mechanism? You have H minus, which will act as a nucleophile, which actually attack this carbon C center. which is actually electron deficient, and this O actually going to O minus. By this actually lithium aluminum hydride works to reduce the carbonyl group. So if you have this compound like this hydrogen has been attached here, one new hydrogen which has came from lithium aluminum hydride, and this has been converted to O minus. This intermediate, now you can see, is the perfect skeleton for quasi-Favorskii, because this bond is actually exactly parallel to this bond. In this form you can see you have O minus. Once more I am saying you have O minus and this bond parallel to this bond. So there is a probability for a quasi-Favorskii. That was actually the expected answer, what they expected from you. So this bond above the plane, so this should be on the plane, because this is also below the plane. So this bond, as it is below the plane, so this will be exactly parallel. So this bond can migrate here and this can leave out, because this is aligned to this bond which is exactly parallel to make it quasi-Favorskii. So this will form this compound, which is actually, now you can understand, you have 1, 2, 3, 4, 5, 6 member ring. Now this bond will leave out here, so this bond will connect this carbon atom. So this will form a 5 member ring. This was a 7 member ring. So one bond has been lived out, so this will form a 6 member ring. This is 6 member ring, this is 5 member ring. Very easy to figure out that type, but the one thing to figure out is quite tricky, that there is another chance of quasi-Favorskii along with the lithium aluminum hydride reactions. Now this will form this type of compound, CHO, because this is O minus, and so this will form CHO, and this will go and attach here. So this will form this type of compound. Now lithium aluminum hydride can reduce this carbonyl group in presence of the unsaturation, what we normally know. So this will form this type of compound. So this was the compound. So this question you can understand is quite tricky, and you never can do these questions in examination if you don't know what is quasi-Favorskii and what is logic behind it. So in next video, that's all for now. In next video we will discuss about 2 more questions on quasi-Favorskii which has been appeared for CSIR and various competitive exams.